Apple just dropped something that's going to fundamentally reshape how we think about artificial intelligence. They've unveiled Fast VLM, a vision language model that's not just incrementally better than what we've seen before, but represents a complete paradigm shift in how AI processes and understands visual information. We're talking about a model that's 85 times faster, 3 times smaller, and powerful enough to run smoothly on a regular MacBook Pro. After 15 years of working in AI research, I can confidently say this is the kind of breakthrough that only comes along once in a decade. But before we dive into why this matters so much, let me paint you a picture of where we've been and why getting here has been such a monumental challenge. Vision language models, or VLMs, represent one of the holy grails of artificial intelligence. These are systems that can simultaneously understand both text and images, allowing you to show an AI a photograph, a chart, a document, or even a screenshot, and have it respond intelligently based on what it sees. It sounds simple enough, but the technical challenges involved are staggering. The fundamental problem that's plagued this field from the beginning is what researchers call the resolution trade-off. If you feed a low-resolution image into your model, it's going to miss crucial details. The text might be unreadable, fine patterns invisible, important context lost. But when you crank up that resolution to capture all those details, you run headfirst into a computational nightmare. Your vision encoder suddenly has to process exponentially more data, generating thousands upon thousands of tokens that then need to be processed by the language model. The entire system grinds to a halt. This is why when you upload a complex image to ChatGPT or Google Bard, you often find yourself waiting what feels like an eternity for that first word to appear on screen. In our industry, we call this metric TTFT, or time to first token, and it's become the bane of anyone trying to build practical AI applications. That lag between input and response is the difference between a tool that feels magical and one that feels frustrating. Apple has been obsessing over this metric, and what they've achieved is nothing short of revolutionary. To understand just how significant Fast VLM is, we need to take a step back and look at how this field has evolved. The earliest vision language systems, models like Frozen and Florence, relied on something called cross-attention. Picture this as weaving image and text information together right inside the layers of the language model itself. The image features and text features would interact at every level, creating rich, nuanced understanding. It worked, but it was computationally devastating. The processing requirements were so intense that these systems could only run on massive server farms. The field then shifted toward what we call autoregressive approaches. Models like Lava, Mini GPT-4, and Cambrian-1 took a different tack. Instead of weaving everything together in the middle, they simplified the process by feeding image information directly alongside text, letting the language model process both streams simultaneously. This was more efficient, and it became the dominant approach across the industry. But even with this streamlined approach, the bottleneck remained stubbornly persistent. The problem was in the vision encoders themselves. Almost everyone was using clip-style transformers, variants like SIGLIP, Intern VT, and DFN clip. These encoders are reliable and well-tested, proven workhorses of the field, but they have a fundamental flaw. They generate an absolutely massive number of visual tokens, overwhelming downstream processing. Researchers tried everything to solve this. Some experimented with pruning techniques, literally cutting away tokens on the fly to reduce the computational load. Others developed hierarchical backbones, systems that would progressively downsample images in stages, trying to preserve important information while reducing data volume. There were even teams like Conalave that threw out transformers entirely, relying purely on convolutional networks for vision processing. Each approach had merit, but they were all essentially band-aid solutions, treating symptoms rather than addressing the root cause. Apple looked at this landscape and decided to go back to first principles. What they've created with Fast VLM is built around a component they call Fast VIT-HD, and it represents a fundamental rethinking of how vision encoders should work. At its core, Fast VIT-HD is what we call a hybrid vision encoder. But don't let that term fool you into thinking this is just another incremental improvement. The way Apple has implemented this hybrid approach is genuinely brilliant. The architecture leverages the strengths of both convolutional layers and transformer layers, but in a carefully orchestrated dance that maximizes efficiency. The convolutional components handle the heavy lifting of image compression, rapidly, extracting local features and patterns with the kind of efficiency that convolutions are famous for. Then the transformer components take over, bringing their sophisticated attention mechanisms to bear on understanding relationships and context across the entire image. What makes Fast VLM truly special is that it produces dramatically fewer tokens than traditional approaches, while somehow managing to preserve the fine details that matter for high-resolution image understanding. The secret lies in Apple's architectural choices. While most hybrid models use 4 stages to gradually reduce image dimensions, Apple added a 5th stage with an additional downsampling layer. This might seem like a small change, but its impact is profound. Instead of the self-attention mechanism operating on data that's been reduced by a factor of 16, it now works with data reduced by 32. That single architectural decision means the encoder runs significantly faster and produces 4 times fewer tokens for the language model to process. But the genius is in how carefully balanced this architecture is. The first 3 stages are built around what Apple calls rep mixer blocks, which are highly optimized for efficient convolutional processing. The final 2 stages leverage multi-headed self-attention, bringing in the transformer's ability to reason across the entire image. Together, this setup delivers both efficiency and accuracy, fewer tokens and less lag, without any meaningful sacrifice in detail or understanding. When I first saw the performance numbers for Fast VLM, I had to double-check them because they seemed almost too good to be true. In direct comparison with the Lava 1.5 setup, Fast VLM achieves a 3.2 times improvement in time to first token when compared against Lava Vision at its maximum resolution of 1152 by 1152 pixels. But that's just the beginning. When you look at the broader comparison, Fast VLM runs 85 times faster on TTFT metrics, with a vision encoder that's 3.4 times smaller in terms of parameters, 85 times faster. Let that sink in for a moment. We're not talking about clever optimization tricks or computational shortcuts that sacrifice quality for speed. This is a fundamental architectural breakthrough that maintains accuracy while delivering these dramatic speed improvements. On the Text VQA benchmark, which tests a model's ability to read and understand text within images, Fast VLM outperforms ConVLAVA by 8.4% across a broad spectrum of challenging benchmarks like Seedbench, MMU, and MMVet. It consistently matches or surpasses state-of-the-art models while generating 5 times fewer visual tokens. Perhaps even more impressive is how Fast VLM stacks up against Cambrian 1, which is widely regarded as one of the strongest multimodal models available, using multiple specialized encoders to achieve its performance. Fast VLM delivers comparable results. While running nearly 8 times faster, this isn't just an incremental improvement. It's a complete redefinition of what's possible in this space. But what really caught my attention wasn't just the performance metrics, it was the training efficiency. Apple managed to train these models on a single node equipped with 8 NVIDIA H100 GPUs. To put this in perspective, most cutting-edge AI research requires massive distributed training across hundreds or thousands of GPUs. Apple's approach is not only more resource efficient, it's more accessible to researchers and organizations that don't have access to enormous compute budgets. The training process itself is elegantly streamlined. Stage 1, the initial training phase, takes just 30 minutes when using a Qwen 27B. Decoder, Stage 105, which involves resolution scaling with 15 million samples, requires about 77 hours when training at 1024 resolution. Stage 2, the visual instruction tuning phase with 1.1 million samples, completes in approximately 8 hours. If you want to push performance even further with 1.5 million high-quality instruction tuning samples, you can achieve additional gains without exponentially increasing compute requirements. This efficiency isn't just about saving money or time, though those benefits are substantial. It's about democratizing access to cutting-edge AI research. When you can train competitive models with reasonable computational resources, you open the door for smaller research groups, universities, and companies to contribute meaningfully. To the field, Apple has essentially lowered the barrier to entry for serious vision language model research. One of the most clever aspects of Apple's approach is how they've handled scaling. Instead of relying on complex token pruning strategies or sophisticated tiling approaches, they realized that Fast VLM's architecture was efficient enough to simply scale input resolution directly. This is a much cleaner solution than the elaborate workarounds that other teams have had to implement. Rather than chopping images into tiles and processing each one independently, which is computationally expensive and can miss important cross-tile relationships, Fast VLM can take a full high-resolution image, encode it efficiently, and maintain low latency throughout the process. They did experiment with tiling for extreme resolutions like 1536 by 1536 pixels and found that it can still provide benefits in those edge cases. But for the vast majority of real-world applications, direct scaling proved superior for both accuracy and speed. This elegance of approach is characteristic of Apple's engineering philosophy. Find the right architectural foundation, and complex problems often have simple solutions. The design of Fast VLM itself reflects this principle of elegant simplicity. It has far fewer moving parts than the massive, complex models that other organizations have been building, yet it consistently outperforms them. On a standard MacBook Pro, it runs nearly 7 times faster than some of the most popular vision transformers while maintaining equivalent or superior accuracy. Even when compared against models specifically designed for efficiency, like Vitamin, Fast VLM manages to be both faster and smaller, achieving better overall efficiency across the board. What makes this even more remarkable is that Apple tested all of these performance metrics on actual consumer hardware, not the kind of specialized server infrastructure that most AI research relies on. They converted the model to run directly on the Mac neural engine, and the performance was consistently excellent. This demonstrates that Fast VLM isn't just a research curiosity or a proof of concept. This is technology that can realistically run on the devices sitting on your desk right now. This brings us to a fascinating strategic question. Why would Apple choose to open source such a significant technological breakthrough? In an industry where competitive advantages are closely guarded, Apple's decision to make Fast VLM freely available seems almost counterintuitive. But when you think about it from a broader strategic perspective, it's actually a brilliantly calculated move. Apple has been building toward a future where artificial intelligence runs locally on devices rather than in the cloud. They've invested heavily in custom silicon designed specifically for AI workloads, from the neural engine in their mobile chips to the unified memory architecture in their desktop processors. By open sourcing Fast VLM, Apple is essentially creating an ecosystem effect. When developers adopt Fast VLM for their applications, they'll naturally optimize for Apple's hardware, creating a competitive moat that's difficult for other companies to cross. Moreover, by letting the community build upon and validate Fast VLM, Apple accelerates the development of applications that showcase the capabilities of local AI processing. Instead of having to develop every possible use case internally, they're leveraging the creativity and expertise of thousands of developers worldwide. It's the same strategy that made iOS so successful. Provide the platform, let developers create the magic. There's also a standardization play at work here. Just as CLIP became the de facto standard for vision language understanding, Apple wants Fast VLM to become the standard for efficient multimodal AI. If they can establish this architectural approach as the baseline that everyone builds upon, they maintain influence over the direction of the field while ensuring that developments benefit their hardware and ecosystem. Perhaps most importantly, this move represents Apple's response to the current AI landscape dominated by cloud-based solutions from Google, Meta, Microsoft, and OpenAI. While these companies have focused on building ever larger models that require massive data centers to operate, Apple is betting on a different future, one where powerful AI capabilities are distributed across individual devices, providing better privacy, lower latency, and reduced dependency on internet connectivity. This philosophical difference isn't just about technology. It's about fundamentally different visions of how AI should integrate into our lives. The cloud-first approach offers certain advantages in terms of raw computational power and the ability to rapidly deploy updates across millions of users. But it also creates dependencies, privacy concerns, and latency issues that can limit the practical applications of AI technology. Apple's device-first approach addresses these limitations head-on. When AI processing happens locally, your personal data never leaves your device. Response times are limited only by local processing power, not network connectivity, and users aren't dependent on internet access or cloud service availability for AI functionality. Fast VLM represents a major step toward making this vision practical and compelling. The implications extend far beyond technical performance metrics. Consider the real-world applications that become possible when you have fast, accurate vision language processing running locally on consumer devices. Instant document understanding becomes seamless rather than frustrating. Instead of photographing a contract or financial statement and waiting minutes for cloud-based analysis, you get detailed insights immediately. Real-time visual assistance for accessibility applications becomes truly real-time, enabling AI-powered descriptions of surroundings without the delays that make such systems impractical in dynamic environments. Educational applications are transformed when students can get instant explanations of mathematical problems, scientific diagrams, or historical documents simply by pointing their device's camera at the material. The difference between a multi-second delay and an instant response is the difference between a useful learning tool and a disruptive interruption to the learning process. In healthcare settings, medical professionals could receive instant analysis of charts, X-rays, or patient information without having to upload sensitive medical data to cloud services. This addresses both privacy concerns and practical workflow requirements in environments where every second matters. But perhaps the most exciting applications are the ones we haven't imagined yet. When powerful AI capabilities become as accessible and responsive as opening a camera app, developers will create use cases that were previously impossible. The combination of local processing, instant response times, and comprehensive visual understanding opens up entirely new categories of applications. However, it's important to acknowledge that Fast VLM isn't a perfect solution to every challenge in this space. Like any technology, it has limitations that users and developers need to understand. While it's dramatically more efficient than previous approaches, it still requires decent hardware to run effectively. Older devices or budget smartphones might struggle to deliver the kind of performance that makes these applications compelling for highly specialized tasks like medical imaging analysis or satellite image interpretation. Domain-specific models trained on specialized datasets might still outperform general-purpose vision language models. Fast VLM excels at broad, general understanding. But there are applications where specialized expertise trumps general capability. There are also the usual concerns about bias and training data quality that affect all machine learning systems. Fast VLM can only be as good as the data it was trained on, and any biases present in that training data will be reflected in its outputs. This is particularly important for applications in sensitive domains like healthcare, law enforcement, or hiring, where biased AI systems can perpetuate or amplify existing inequalities. The current version also has limitations around context length and complex multi-image reasoning. While it excels at understanding individual images in detail, applications that require reasoning across multiple related images or maintaining context across extended visual conversations may still challenge current capabilities. But these limitations don't diminish the significance of what Apple has achieved. Rather, they represent the natural boundaries of current technology and point toward areas for future development. The architectural foundation that Apple has established with Fast VLM provides a solid platform for addressing these limitations as the technology continues to evolve. For developers and businesses looking to leverage these capabilities, Fast VLM opens up tremendous opportunities. Applications that previously required expensive cloud infrastructure and resulted in ongoing API costs can now run locally, reducing operational expenses while improving user experience. Computer vision applications, document processing tools, educational platforms, accessibility aids, and countless other categories of software become more practical and accessible. The barrier to entry for AI-powered applications has been significantly lowered. Small development teams can now build sophisticated vision language applications without needing to negotiate enterprise contracts with cloud AI providers or worry about scaling costs as their user base grows. This democratization of AI capability is likely to drive innovation in unexpected directions as creative developers explore what's possible with these new tools. From a business perspective, the shift toward local AI processing addresses several persistent challenges with cloud-based approaches, data privacy concerns, which have limited AI adoption in sensitive industries, become much more manageable. When processing happens entirely on device, latency issues that make certain applications impractical disappear when you eliminate network round trips. And the ongoing operational costs associated with cloud AI services are replaced with one-time implementation costs. Looking toward the future, I expect Fast VLM to catalyze developments across the entire AI ecosystem. Other hardware manufacturers will likely optimize their processors for efficient vision language processing, creating a broader ecosystem of devices capable of running these models effectively. We'll probably see specialized accelerators designed specifically for hybrid architectures like Fast VLM. On the software side, I anticipate rapid development of applications that take advantage of these new capabilities. Mobile apps will integrate sophisticated visual understanding as a standard feature rather than a premium add-on. Web browsers might develop native support for vision language processing, enabling entirely new categories of web applications. Operating systems will likely integrate these capabilities at a fundamental level, making visual AI as ubiquitous as text processing is today. The competitive response from other major technology companies will be fascinating to watch. Google, with their heavy investment in cloud-based AI services, faces a strategic challenge. They'll need to pivot toward edge computing capabilities to remain competitive, which may require significant changes to their current business model and technical infrastructure. Meta, given their focus on augmented and virtual reality applications, has perhaps the strongest motivation to develop competing efficient vision language models. AR and VR applications are fundamentally dependent on low-latency visual processing, making cloud-based solutions impractical for many use cases. Microsoft finds itself in an interesting position. Having bet heavily on Azure-based AI services while also maintaining significant hardware partnerships, they'll need to balance their cloud infrastructure investments with the growing demand for edge AI capabilities. NVIDIA, perhaps counterintuitively, stands to benefit regardless of which direction the market moves. Their processors power both cloud-based and edge AI applications, and the growing demand for efficient AI processing is likely to drive hardware upgrades across both domains. To truly appreciate the technical innovation behind Fast VLM, it's worth diving deeper into those rep mixer blocks I mentioned earlier. These components represent a sophisticated evolution of traditional convolutional processing that addresses fundamental limitations in how visual information is processed. Traditional convolutional layers excel at extracting local features from images. They're computationally efficient and very good at detecting patterns like edges, textures, and simple shapes, but they struggle with understanding relationships between distant parts of an image. Pure transformer architectures, on the other hand, are excellent at modeling long-range dependencies and understanding global context, but they're computationally expensive, especially for high-resolution inputs. Rep mixer blocks find an elegant middle ground. They use sophisticated mixing operations that capture local patterns more efficiently than traditional convolutions, while maintaining enough context awareness to understand how different parts of an image relate to each other. This allows Fast VLM to process visual information with the efficiency of convolutional networks while maintaining the contextual understanding capabilities that transformers provide. The privacy implications of Fast VLM extend far beyond simple data protection. When AI processing happens locally, it enables applications that would be impossible or impractical with cloud-based systems. Medical professionals can analyze patient images without transmitting sensitive health information across networks. Legal professionals can process confidential documents without exposing client information to third-party services. Financial advisors can analyze personal financial documents while maintaining complete confidentiality. This privacy-first approach isn't just about compliance with regulations like GDPR or HIPAA, though those benefits are significant. It's about enabling trust in AI systems by ensuring that users maintain complete control over their data. When people know that their personal information never leaves their device, they're more likely to engage with AI applications in meaningful ways. For For the research community, Fast VLM represents both a destination and a departure point. Apple has demonstrated that architectural innovation can deliver dramatic improvements in efficiency without sacrificing accuracy. This success will likely shift research priorities across academia and industry, with more attention paid to efficient designs rather than pure accuracy optimization. The open-source release of Fast VLM means that researchers around the world can build upon Apple's work, potentially leading to even more efficient architectures. We're likely to see a flowering of research into hybrid approaches, novel attention mechanisms, and specialized processing techniques inspired by Apple's success. But perhaps the most significant impact will be cultural. For years, the AI research community has operated under the assumption that bigger is better, that more parameters and more compute always lead to better results. Fast VLM challenges that assumption directly, showing that thoughtful design can outperform brute force scaling. This could herald a new era of AI research focused on elegance and efficiency rather than raw size. The democratization aspect of this technology cannot be overstated. Currently, the most powerful AI capabilities are concentrated in the hands of a few large technology companies with the resources to build and maintain massive cloud infrastructure. Fast VLM points toward a future where sophisticated AI capabilities are distributed across billions of individual devices, fundamentally shifting the balance of power in the technology ecosystem. Imagine a world where every smartphone, laptop, tablet, and IoT device has sophisticated AI capabilities built in, where AI assistance is always available, regardless of internet connectivity, where personal data never needs to leave personal devices to benefit from AI analysis, where the cost of accessing AI capabilities is limited to the initial hardware purchase rather than ongoing subscription fees. Fast VLM brings us significantly closer to that vision. It's not just a better AI model. It's a proof of concept for a fundamentally different approach to how AI can be integrated into our daily lives. The technical achievement is impressive, but the broader implications are revolutionary. The timing of this release is also significant, as concerns about AI safety, privacy, and concentration of power in the technology industry continue to grow. Apple's approach offers a compelling alternative. Local AI processing addresses many of the concerns that have made people wary of AI adoption while delivering superior user experiences in many contexts. This represents Apple at its best, taking complex technology and making it accessible, elegant, and user-focused. Just as the iPhone transformed mobile computing by combining existing technologies in new ways, Fast VLM has the potential to transform AI by making powerful capabilities accessible on personal devices. As we look toward the future, Fast VLM stands as more than just a technical achievement. It represents a vision of AI that's personal, private, and powerful. It suggests a future where AI capabilities are as fundamental and accessible as any other feature of our computing devices. And it demonstrates that the path forward in AI isn't necessarily about building bigger models, but about building smarter ones. The companies, developers, and researchers who understand and adapt to this shift toward efficient local AI will be positioned to lead the next wave of technological innovation. Those who remain focused on cloud-based approaches may find themselves increasingly marginalized as users gravitate toward AI experiences that are faster, more private, and more reliable. Fast VLM isn't just Apple's latest AI model, it's a glimpse into the future of computing itself, where artificial intelligence is seamlessly integrated into every aspect of our digital lives without compromising privacy, performance, or accessibility. That future starts now.